Okay, let's start. Good morning. So today I'm going to take attendance. Let's start from here. So I guess I should mention, that's the attendance sheet. I want you to write your last name, first name, and then put your signature or initial, whatever. Okay. So problem set 1. I had uploaded on Canvas on Friday, and I realized some of you already started working on it, which is what you should have done. So before I continue with the topics and stuff, I wanted to ask you, are there any questions or comments?
The one about finding out what values of b would make the equation non-existent. Are we supposed to be able to do that yet?
Oh, yes.
We are able to do that with
Yes, yes. Now, one of the things that's going to happen in this class is, probably most of you are familiar with doing calculations with numbers, but eventually we're going to start doing calculations with, variables or parameters. So eventually, you're going to start manipulating algebraically letters ultimately. Now that's sort of like, that requires sort of switching to the next step somehow. It's somewhat more abstract. So if you're struggling with even starting with something like that, so for instance, your colleague was mentioning problem 3. In problem 3, they give you a 3 by 3 matrix A and a 3 by 1 matrix B. Okay, A is a numerical matrix. It has 9 integer entries, whereas B is an arbitrary. It's an anonymous 3 by 1, B1, B2, B3. Your colleague is asking, so the question is asking, describe the set of all B's for which AX equals B does not have a solution, inconsistent. So A is numerical. Find all B such that AX equals B is inconsistent. That's the problem. Well, how are you going to handle this? Well, we pretty much do one thing first, right? We put it in an augmented matrix, reduce it as much as possible. You want to get as many zeros as possible on the left-hand side. And then we know one of the tricks, right, about figuring out if a system is inconsistent, which is when in this augmented matrix notation, you have zeros on the left-hand side, whereas a non-zero on the right-hand side. Okay, that means that you're going to reduce this, get something, okay, and then based on the shape of the left-hand side that you need to calculate numerically, you're going to figure out which entries of B, if non-zero, would kill the game. Okay, would make it inconsistent. So what you're trying to get is one row such that, using the notation in the textbook, I should put a square like this. We're going to talk about this notation today. Okay, so you're trying to do some row operations with this to get something like this. Does this make sense? Yeah. Okay. Any other questions or comments? Yeah.
In problem 5, when you go up to Wolfram and recording some values, some of them will not appear on Wolfram.
Say again?
So in problem 5,
yes.
you go to Wolfram,
yes.
and then you're recording some values
yes.
in the matrix.
Yes.
Some of the value that is not appear on Wolfram.
Okay, then that's what you record.
Okay, so no.
Yeah, I mean, your colleague is suggesting something legitimate, so maybe it doesn't say, this is the determinant, whatever, for some matrices. Now, it might be the case that you actually need to explicitly say to Wolfram, compute the determinant of this. Okay, sometimes it's going to do it automatically, and sometimes, of course, this is not random, of course, but you know, part of it is you getting used to opening up Wolfram to get some numerical data. Yeah. Another thing too, this sometimes gets confusing. If you right now go to Gradescope, okay, there's a web page for Gradescope where, for our course, where you're going to submit things, you're going to see problem set, code, I don't know, it's like potato, or code apple, all these kind of things. So it's not going to be clear where you're going to submit the problem set. That's because I want you to always use this problem set specification. So use this link. You can click on it. Okay, it's going to take you to the right assignment page. Okay, and that's because I don't want you to skip this, fill out this form part. Okay, this is so that you don't get to say, oh, I didn't see this. I didn't see, I should have submitted the form. So everything is going to go through the specification documents. Okay. And another thing, for instance, on Gradescope, if you look at it, it's like all problem sets start on January 4th, I think, and end on like April 20th. These are not the deadlines, okay? I just didn't bother plugging in the deadlines because I did that on Canvas, but the APIs of these two web pages, they just like don't work together for some reason, okay? And they decided not to fix it. And I refused to just change one thing and then manually change the other one. It's like, then what's the point? What's the point of this learning system? So everything is here. Everything is in the specification documents. Deadlines, everything, okay? Links. Okay, that's that. Any other comments or questions? Yeah?
I believe I sent you an email about this, but I just want to further clarify. So when we were doing matrix examples in class last week, we used integers and only integers for tests and problem sets. Are we expected to use fractions if needed?
Okay, let me put it this way. So I think, were you the one who sent the email?
I think I did.
Okay, yeah, so your colleague is suggesting this. So in class, I made this comment, oh, here's a matrix with integers, and some of your colleagues suggested, I don't know, let's take this and subtract it from this or whatever. Something happens. Or let's say that, okay, look at the first row here and scale it by 1/3. What was the number? -6. So that you have a 1 here. But then that would mess up this guy and this guy by turning it into 4/3 and stuff. I said, don't do this because, I suggested that you don't do it, but when I do make a suggestion like this, that's not a requirement, okay? You can just do it however you want. I'm just trying to be a little bit more transparent as to what my thought processes are, okay? I don't like 4/3. Okay, so if I were to give you this in the exam, it's all valid. You can do whatever you want. Okay, you can scale the first row by 1/pi if you want. Okay, I don't care, insofar as it works, of course. But so it's yours to decide in a sense.
So on tests and other stuff, it will always be possible to do it without fractions?
No. No. That's too much for me to promise. Good point, though. I will try to come up with as nice matrices as possible, but every once in a while, things happen. Okay. Yeah. Any other comments or questions?
I was going to say, so on problem 2, it's asking you to what can you assume about these sum variables, these sum coefficients, given that f and g work for all real numbers. Is that just asking us to find some bounds, something like, hey, what could this not be, or what does this have to be? Is that what it means to say something about these coefficients?
Yeah, you see, this is one of those problems that the people who took this class from me last time also, objected. This problem essentially comes from the textbook. That's why I kept it there. I almost sort of changed it how it was stated. What can you say? I dislike these type of problems. I cannot say anything. It's is that a valid answer? It's The point is that you want to come up with some sort of general formula, perhaps. Can you come up with a formula that A, B, C, D is supposed to satisfy? Okay. Yeah, for instance, like, so this was a problem 3. Problem 2, suppose A, B, C, and D are constants such that the system below is consistent for all possible values of f and g. So ax plus by, cx plus dy equals f equals g. Instead of x1, x2, I'm just going to use x and y. Okay? But you want this to be consistent for all f and g. Then you're asking, what can you say about A, B, C, and D? So for instance, this cannot happen. Let's write it like this. Um, 1, 0, 1, 0. For instance, this cannot happen. Does this make sense? Why can it not happen? Because for these specific numerical values of A, B, C, and D, this system reduces to x equals f, x equals g. But then this system does not have a solution for all f and g's. It's kind of bizarre to say, but if I were to, for instance, plug in f equals 1, g equals 0, this has no solution now. It's kind of backwards in a sense. Does this make sense?
That's just because you can reduce that to f equals g.
Exactly, yes. Yes, you can think of it that way as well. So you can sort of test out a bunch of numerical things and then try to do row reduction on ABF CDG. Okay, this is where things get a little bit more abstract. I would suggest doing some sort of a case analysis here. Okay, I would say something like, okay, so there's nothing distinguishing A, B, C, and D in my eyes. These are just anonymous numbers. But I can do a case analysis. Okay, I can say either A is 0 or it is not. If it is 0, then I would look at this guy. Either C is 0 or it is not, blah, blah, blah. For instance, if A were non-zero, I could use it to get rid of this guy. Right? I would divide the first row by A and subtract it from this, or multiply the first row rather by C over A and subtract it from here to get rid of this guy. Things like this. But you need to assume things. Okay? You don't know anything about these 4 numbers. Now, this looks like an abstract mathy stuff, but even for applications, something like this ends up being very important. Because it turns out that maybe in general you don't have 4 parameters, but maybe you have 1. Maybe 3 of them are fixed. Because why? Somehow these matrices come from a certain application. You have a certain model that you're using to come up with some prediction as to what happens eventually. But the point here, of course, is that in your model, some of the variables you want to leave as tunable parameters. This is what you do, for instance, in LLMs. You don't know exactly what number fits best to the data that you have. So you want to keep it as a parameter. And perhaps, depending on the outcome, sort of engineer the proper choice. Okay? So being able to calculate things, or calculate or manipulate letters as if they are numbers, ends up becoming a very important thing for applications. Also for pure math purposes, of course, but this class is mostly about like being able to use these kind of matters. Okay. So a couple of things I want to do today. I want to first do one more example. We were some of your colleagues already made some comments about the possibility of what this is going to exemplify. And then I want to really talk about these echelon forms and reduced echelon forms. I'm not going to give the specific definition because the specific definition, which you can read in the textbook, is rather sort of poetic as far as I'm concerned. I'm going to give you the list pretty much for echelon forms in low dimensions. Okay. So, okay. And even before that, I want to mention one thing. What is the significance of this bar here? Now, if you look at the textbook, this example is from the textbook. In the textbook, they just say, row reduce this. Okay? And they don't draw the line here. Now, let's first understand that this is a valid thing to do. If I were to give you an arbitrary matrix without it being actually coming from a system, you can still apply these row operations that we were discussing to make it as simple as possible. Okay? That's the first observation. Second observation, when we're doing these row reduction business, actually drawing this line here has no meaning or ramification whatsoever. If I wanted, I could have just erased this, and I can just do the same row reduction business. Okay? Does this make sense? So this perhaps justifies a little bit why in the textbook they don't draw the bar and I do. It doesn't matter ultimately. In a sense, it's all in your head. Okay? But also, there is this idea of blocking or partitioning a matrix. And this augmented matrix notation that I'm using over here with the bar is an example of this. And I kind of mentioned this as well last week. Initially, we would like to imagine matrices to be arrays of numbers. But in principle, there's nothing stopping you from thinking of arrays. Okay? So in principle, I can also think of this as a 1 by 2 matrix, where the first entry is a 3 by 5 matrix, and the second entry is a 3 by 1 matrix. Okay? Now, this is all in my head. Doesn't matter. It's like these are the numbers. Doesn't change. Okay? But somehow, it ends up being important to be able to think of different parts of perhaps a numerical matrix as sort of like one entry in and of itself. This we're going to sort of see the ramifications of later. But let me say, idea of blocking. So, can think of star as a, what was it? 3 by 6, right? 3 rows, 1, 2, 3, 4, 5, 6 columns. Number of rows always comes first, 3 by 6. As a 3 by 6 with numerical entries. Or, you see, I say to myself, I'm just going to think of this left-hand side as one thing, and the right-hand side as another thing. Or a 1 by 2 with one entry, 3 by 5, and the other entry, 3 by 1. 3 by 1. Okay. So I kind of mentioned how you should think of augmented matrices or matrices in general, sort of the world of computers, but you should imagine it as sort of infinite compute and infinite memory, okay? You can just keep putting things in. And this idea is going to come in handy later. Okay. Any comments or questions about this? Now slowly, you see, we're going to start seeing the structure. So the numbers are not really that important. Somehow there's a structure underneath, and we're trying to get to that really. Linear algebra is all about sort of leveraging that structure. And so in terms of notation too, I can write it like so. Remember to denote that A is 3 by 6. I wrote like so. Okay, 3 to the left, 6 to the right. Or you can think of it like so. A, 3, and then 5, 1. Okay. So now I'm saying, I'm partitioning the columns into the first 5 columns and then another column. Okay. These are just like, these are going to come in handy later. Okay. Any comments or questions about these? These are just general sort of philosophical almost statements. Now, when I write solve this, really I mean the system that is associated to this, but I didn't bother writing it down. Okay? I'm going to leave that to you. We were doing it one way. Turn this into a system of equations. Okay? Write the system of linear equations corresponding to the augmented matrix given. Corresponding to this augmented matrix. Okay. Just to get some practice. And so now let's reduce it. What was reduction? Well, we have 3 different operations we can use. One of them is scaling. The other one is replacing. Third one is interchanging, right? And by using these 3 operations in succession, I want to simplify this expression as much as possible. And what do I mean by simplify? On the left-hand side, I want to see as many zeros as possible and as many ones as possible. Okay, so we're just going to do that. Let's see. Maybe I should ask you, what would you suggest?
My first step was I did row 2 turns into row 2 minus row 3, and then after that I did row 2 is half row 2, and then row 3 is a third of row 3.
Okay, so your colleague is suggesting, well, I can get rid of this 3 using this. Why not the other way around? Maybe you can tell me.
Because the row 3 right now is all divisible by 3.
Okay.
And we'll mess that up.
Right, so they don't mention these kind of things in the textbook, but you want to sort of start seeing patterns. That's the one thing that I noticed as well. I'm saying, oh, there's a 0 here. That's a good one. That's a good thing. And so there's a 3 here. I can try to turn it into a 1, but then this is gonna get messed up. So I'd rather keep that for now. And I say, oh, I can use either one of these to get rid of the other one. But then this third row is better than the second row because everything in the third row is divisible by 3. I'd rather keep that symmetry, I say, just like your colleague. Okay? So instead of getting rid of this 3, I want to get rid of this 3. Okay? By the way, in the textbook, they mention this algorithm. Okay? First start with this, always look at this, blah, blah, blah. You can use that algorithm as well. The textbook, I think, is somewhat misleading because it kind of, once you read it, it kind of sounds like that's what computers do. But technically, when it comes to using a computer to actually do row reduction, there are more technical matters, because technically with a computer, you don't actually have real numbers, you have floats, which means that you have to actually worry about losing information when you're dividing and stuff like that. So it's up to you, okay? I'd rather you sort of see the structure of the matrix you're trying to reduce and try to sort of use the structure instead of doing this algorithm. The benefit of using the so-called algorithm is that you don't need to guess. You don't need to sort of think that much. Okay, that's also valuable, of course, in certain circumstances. Okay, so what are we going to do? Replace row 3 by row 3 minus row 2. Okay, same thing like as we did last week. That's that. And then this. So now I need to figure out what I should be putting here. So that's going to be a 0. That's a 2. That's a minus 4. That's a 4. That's a 2. And then that's a minus 6.
I was like, don't you mean you replaced row 2 and not row 3?
Yes, thank you. Very good. Yeah. Was that also what you were going to say? Okay. Apologies. Okay, so now we're in a better situation because we have some symmetry in the third row. Everything is a multiple of 3. But also we have some symmetry in the second row. Everything is a multiple of 2. So let's use those. I'll do both of them simultaneously. Okay, and then like so. Okay. That's a 0, 1, minus 2, 2, 1, minus 3. And then 1, minus 3, 4, minus 3, 2, and 5. Okay. That's nice, because now, you see, I can use this guy to get rid of this minus 3. Okay. So row 3 is replaced by row 1 plus row 3. And the outcome is this. Is that. That, and then 1, 0, I'm just adding both of them. Minus 2, 3, 6, 10. Okay.
I think you made, on the very first problem,
It should be R2 minus R3, the first one.
This one?
Yeah.
Okay.
It should be R2 minus R3 because I see what you did.
yes.
Oh, okay. So there's a minus here and plus here. Okay. Thank you. So that's that. Any suggestions as to what to do now? Someone else?
So now we can replace row 1 with row 1 minus 3 times row 2.
Yes. Why? Because I told you ones are jokers, okay? Use this, and there's nothing before. So if I were to use this to get rid of this, this is not going to get messed up. That's why I use this row 2, multiply it by minus 3, and add it to the first row. Okay, so minus 3 times row 2. Okay. So first record this. And this. So now I have 0 here. That's also 0. So I need to multiply it by 3 and then subtract. Okay. Minus 6, minus 12, minus 6, 0, minus 3, 1, 9, 14.
Your negative 12 should be 0, I think.
Yeah.
Oh, I made a mistake. Okay. Oh, yeah, it's the other way around. Okay, that's a 0. Minus 3 now. That's 12.
And it's also 0.
Yeah, 0.
Oh, yeah. Very good. Okay. Okay. What else can we do? Well, I can use this guy to get rid of these two. Let's do that too, perhaps, to simplify it further. So R2 replaced by R2 minus R1, and then R3 replace R3 minus 6R1. That's what I want to do. Which leaves me with this. Okay, and then 0, 1, minus 2, 2, 0. Subtracting, so that's minus 17. And then this is 1, 0, minus 2, 3, and then minus 6. So I want to do that on the side. If I multiply these two, I get 4 here, 2, and then 8. Subtract 84, that's minus 74. Okay, seems to be correct. And perhaps we can do one more thing, which is this interchange. Remember why? Because I want to go to this echelon form, and what was the heuristic idea of the echelon form? You want to see downward stairs, okay? Finally, replace 1 and 3, rather, interchange 1 and 3. To get this. That should be 0. Zero minus 74, 0, 1, minus 2, 2, 0, minus 17, and then finally 0, 0, 0, 0, 1, 14. Okay. Now this, I tell you, is in reduced echelon form, okay? I'm going to give you a better sense in a second, but where is the staircase I'm seeing? I'm looking at the leading entries that are non-zero. They are sort of in this direction. And this is the staircase I'm seeing, okay? Reduced echelon form. Why is this in reduced echelon form? The idea is, even though there's a bunch of non-zeros and non-ones on the left-hand side, I actually cannot touch these. I cannot make this left-hand side any better. Okay? I can try sort of perhaps using this to get rid of this whatever, but then I'm going to get rid of the, I'm going to mess up this guy. Okay? So now we're here. And now we want to switch over to actually writing the solution. Well, let's cash out. Again, let's say x1, x2, x3, whatever. Okay? So this is the same thing as saying x1 minus 2x3 plus 3x4 equals minus 74. Just to be clear, I'm using these variables. What you can do is you can write on each column the name of the variable you really mean. So x1, x2, x3, x4, x5 if you want. Then I have x2 equals, or x2 minus 2x3 plus 2x4 equals minus 17. And then I have x5 equals 14. Okay. Now, in terms of matrices, you cannot go any further. You cannot make it any simpler. Meaning, you cannot also reduce this system any further than this. But you see, last week I mentioned to you, sometimes solving a system is not necessarily going to mean actually giving specific numerical values to each unknown. This actually is as far as you can go here. The problem here is that, like, what is x1 then? It's a number. Okay? In such a situation, what you say is this. Okay, so x5 has to be 14, but what about x1 and x2? These equations really mean that two of the variables out of x1 to x5 are what are called free. We're going to call these free variables. And so really when we finish this, I want to say also x3, x4, free. So my system really doesn't contain any information as to how I should be choosing these x3 and x4. Okay, go ahead.
How do you know it was x3 and x4, not x1 and x2?
You could have done it that way too. It's just easier because this reduced echelon form, when you switch over to the system notation, turns into this, which then allows you to simply say x1 equals whatever, x2 equals this, and so on. So, in other words, ultimately it doesn't matter what you call free. What really matters is that two of the 5 variables is free.
So, like we were doing before you introduced the matrices, where we would like take the negative 2x3 and the plus 3x4 to the other side. So we have like x1 equals something because that depends on x3 and x4. Is that
Yes,
free?
yes.
Okay.
Saying this really means I don't have specific values for these 5 numbers, for all 5 of them. For one of them I have a specific number. But the moment you say x3 and x4 are free, and these are the only free variables, you really mean once I fix numerical values for these 2 guys, all other variables are also fixed. Their numerical values are determined completely.
Does the number of free variables, is that dependent on the relationship of your columns and rows, or like unknowns and equations?
Yes.
If you had an additional row, would there be one less free variable?
Not necessarily.
Okay.
Not necessarily. The relationship is this, okay? Going back, remember I told you the first thing you should always record when you see a system of equations is the number of equations and the number of unknowns. In this case, we have 3 equations and 5 unknowns. Okay? So already you should sort of start being, suspicious. Something is going wrong here in a sense. Now the pattern is this, okay? There are 3 steps here in this specific reduced echelon form. In other words, there are 3 rows with non-zero leading entries. These we're going to call pivots. Okay, these specific steps, this entry, and this entry, we're going to call pivots. So the number of pivots, in other words, the number of steps in your reduced echelon form is the 3rd important number. That is what's called the rank. Okay? And the number of free variables is always going to be number of variables minus rank. Okay? So somehow these two being free correspond to the fact that in your echelon form, these are not pivots. Okay? Okay. Now, in the textbook, they introduce a bunch of terminology, parametric notation, this notation, that notation. I don't really care, okay? Like, just look at the textbook, I would suggest at this point. One of the notations is going to sound nicer to you. Just take that and use that, okay? This is the notation I like. This is perfectly sufficient. In the exams and stuff, I'm never going to tell you state the solution in specifically this way, okay? Just choose a way of writing this down and use that. Okay. Now, just to reiterate, another way of saying this, that x3, x4 being free signifies that once you fix numerical values to these two variables, all other variables have numerical fixed values also. For instance, I could say perhaps x3 equals 0, and so is x4. Put x3 equals 0 equals x4. Then x1, well, I'll write it like this. Then x, the matrix with entries unknowns. Okay, this is what? Minus 74, minus 17, 14 here, 0, 0. I chose, okay, these three variables to be this specific numerical value, plugged it into the solution, solved for x1 and x2 and so on, and that gave me a solution. I'm saying this is a specific numerical solution to that system. Okay, so exercise, check. Check that this indeed solves the system that you're going to get from this. Plug it in, verify. If I were to use different values for x3 and x4, for instance, x3 equals 1, x3 equals 1, x4 equals minus 1, let's say. These are free. I get to choose them whatever I want. You see, based on these equations, the values of x1 and x2 would change. I would get a different tuple, we're going to say, of numbers. And that too is going to be a solution. So in the previous example so far, we solved the system and we came up with a unique solution. This time we have multiple solutions that are not the same. Okay, this is going to happen. And really this week is going to be all about switching over to a more geometric interpretation of what is actually happening to really make sense of this phenomenon of having multiple different solutions.
Just so clarifying, when we do say a problem set with a question like this, well, I want to start for free variables. Are they going to be the ones with constants in front of them that aren't 1? Like when we go through and solve, and we have, say, x1 was -2 and x4 was still 3. Would x1 and x4 be our free variables? Like this? Like is it the value for the variables without a 1 in front of them?
Exactly, yes.
Okay.
Yes.
And then when we go to check our answer, say we plugged in 1 for each one, what we then just do is take the constants we get from, say, -2 times 1 and then just reduce it.
Yes, yes, yes. Very good. Okay. Any other comments or questions? Okay. Let me check the time. Still trying to get used to this stop. Okay, we have 5 minutes. I think just enough time to introduce echelon forms and reduced echelon forms. I like looking at reduced echelon forms first because they are sort of like simpler in a sense. Just leave it here. Now, this is a notation they use in the textbook as well. Now I want to abstract out the shape of this matrix, and I don't want to worry about the specific values of these numbers here. Okay? Ones and zeros are important, the rest are not that much. And in fact, even zeros above the staircase are not that important. And so the notation is this, okay? A box means a non-zero number that is anonymous. And a star is a number that is possibly zero, anonymous number. For each dimension, you fix a number of rows and columns. There's a certain list of all possible reduced echelon forms you can obtain. Okay? So for instance, more abstractly, I would write this like so. What is important is the number of these pivots. Like so, and then 0. Oh, that should be a 0. 1. Okay. So I keep the staircase like this. The fact that this is a 0 is important because it's above a pivot. Whenever I have one of these staircases, I want the only non-zero entry to be that pivot. I want this to be 0, this to be 0. These specific 4 numbers, I don't really care. This is 1, everything above is 0. Okay, I want to keep it like this. And this right-hand side, I don't care as well. So, let's start one by one. If I have a 1 by 1 matrix, in other words, it's just one number, you have exactly 2 shapes. Okay? Either that single number that is in your 1 by 1 matrix is a non-zero number, or it is a 0 number. It is the 0 number. If it is the 0 number, then there's nothing to do. Okay? It's already 0. Or if it is non-zero, then you can multiply that matrix by 1 over that number to row reduce to get 1. Okay, here's the staircase, and here's the staircase. Okay, 1 by 2. 1 row, 2 columns. Okay, again, it could be like this, or it could be like so. Or it could be like so. And what do I mean by this? I mean, take an arbitrary 1 by 2, row reduce it. Okay? When you row reduce it, you're going to get to exactly one of these forms and no other, is what I'm saying. So we're going to keep talking a little bit more about this echelon forms tomorrow. This is an important sort of structural matter. But that's going to be it for today. Thank you. Okay, let's start. Good morning. So today we're going to keep working on these echelon forms and reduced echelon forms. I would like to give the list of all echelons, at least for low dimensions. I want to try to be a little bit more clear as to what this pivot means. Then we're going to switch over to like a more geometric language, and that's where the notion of a vector is going to come into play. So essentially, vectors are one of the three main actors in this class. Vectors. I'm going to talk about this notation later and this one as well. So this is the first major actor. The second major actor is matrices, and then the third major actor too we're going to introduce this week. And this is what is called a linear transformation. Let me write it this way. Linear transformation. This, like so. I'm going to tell you more about this notation later. So somehow these are all interconnected. Okay. We'll talk about these later this week. So we have two types of echelons. One of them is standard echelon and the other one is reduced echelon. And what are these? Intuitively, these are basically matrices that are reduced as much as possible and organized in a nice fashion. Okay. Once you pick your dimensions for the matrix, there are only so many of these forms. Okay. So if I start with a 1 by 1 matrix, this is kind of bizarre to say, but 1 by 1 matrices are nothing but arrays that contain only one number. This is something you can do. There are two possible reduced echelons. Either it's 0 or it is 1. Okay. So imagine a 1 by 1 matrix. It has only one number. I'm saying just reduce it as much as possible. Either this number is 0, in which case there is nothing to do, or it's a non-zero number, in which case you can just simplify it to turn that whatever non-zero number you have into a 1. Okay? These are the simplest cases. And if you can reduce your matrix to one of them, you cannot reduce it to another one. Okay? So somehow this reduced echelon form is unique, given the matrix that you started with. With 1 by 2, I have one row, 2 columns. Remember, when I'm saying m by n for a matrix, m, the first number, is always the number of rows. And then the second number, n, is always the number of columns. So now I'm looking at a 1 by 2 matrix. Again, it could just be 0 everywhere. There's nothing to do in this case. Or depending on the other entries, it could be like so or like so. When I put this star notation, and this is what they use in the textbook as well, this star means it's some number that I don't know about, that I cannot do anything with. It could be 0, it could be non-zero. Okay, that's what this means. These are as far as you can go when it comes to a 1 by 2 matrix. Yeah, question?
So last time you also mentioned boxes, which is anonymous non-zero numbers, correct?
Sorry, say that again?
Box things?
Yes, boxes are different. Boxes are also anonymous in that sense, but boxes cannot be 0. Yes?
So, related question there. On the example that you showed last time, we put in stars on numbers that were not 0. Would boxes be acceptable there?
Yes.
Why would we not use them then?
You could. I mean, when I'm using this star, I'm saying, in a sense, psychologically to myself, I'm actually not keeping track of whether or not something is a 0. Yeah. Yeah. I hope it will make more sense in a second once I switch over to the echelon forms. 1 by 2s. And remember, I was talking about these staircases. The point of an echelon is the staircase is going this way. So you start from the top left corner of your matrix. You try to go all the way to the bottom right corner. So that's my staircase, for instance, like so. And then that's my staircase. Could be like this, could be like this. Okay? With 1 by 3, again, I have, so these are the all possible options. Either it's like this, and so on. Okay? Does this make sense so far? Okay. Now I'll leave it to you to write down the list for 1 by n. Okay. So now I want to fix the second entry, second dimension to be 1, and try to sort of change the first entry. Okay? But exactly the same thing happens, okay? So let's go here, for instance, instead of 1 by 2, I want to look at 2 by 1. And all I need to do is to flip either this, or this, or this. Okay? Except not, because you have to do things with these, okay? So this is not an echelon form. Whenever you see something like this, you want to interchange the rows so that one is up top. You're always sort of like changing things to get this staircase pattern. And likewise here, you don't want to say, oh, this is some number that I don't know anything about. You say, I could just simplify this a little bit further and just row reduce to get rid of this, whatever this number is, turn it into a 0. Okay? So really, there's only one more here, 1, 0. Okay? So this is 2 by 1, and then let's do 3 by 1. Again, you can have all zeros or one non-zero. That's it. Okay. Does this make sense? Again, I'll leave it to you to write down n by 1s. Things get a little bit more complicated when both of these dimensions are larger than 1. Okay? So for instance, let's look at 2 by 2. What are possible forms, reduced echelons in 2 by 2? I have all zeros. With a staircase like this. And now you see I take the staircase and I'm sort of like folding it to get like more steps. Technically, you want to have more steps, as many steps as possible. The more steps, the better. So I could have something like this, or something like this. Okay. But I could have one more, namely instead of having a 0 here, if I had a 1 there, I would get this guy. Okay. I'll do one more, maybe 2 by 3. I'll do it here. Two rows, 3 columns. Again, I start with the 0 matrix, like so. Okay. So in a sense, I'm thinking to myself, oh, this is the form with, let's say, 0 steps. I'm thinking of this, and it just drops from here to there. Okay. Now I'm thinking of the forms with exactly one step. Well, it could be like so, or like so, or like so. These have all single step. Okay. Or I could have two steps. This doesn't really allow me to do one more, but for instance, I can put a 1 here, and I can put a 1 here or there. And so in which case, this turns into this. Like so, or this, or like this. Okay. Any comments or questions about these? Now you're going to realize I have in fact used a certain, how to say, order in the way I was writing these. Namely, I really sort of separated for each dimension these different forms based on the number of steps. The number of steps is a third important integer that we're going to need to keep track of. Number of rows, number of columns, now the number of what we're going to say stairs or pivots. Okay, so that's the technical word for it. Pivot entry you can say, or pivot column you can say. So pretty much the same thing. Steps in the staircase. Okay. So you see this is somewhat different from the number of rows and columns in a sense, because the number of rows and columns, you can just look at it, look at the matrix and see immediately. This third number, number of pivots, again, I'm telling you it's an important thing, that probably you're not going to be able to see just by looking at it, looking at the matrix. You're going to have to do some calculations. Okay? The number of stairs, or the number of steps in the staircase, when you reduce your matrix, is what is called the rank of the matrix. So I'll write that too. So definition, rank is the number of pivots. This is the R number. So I'm saying, oh, this has R number 0, this has R number 1. 0 steps, 1 step. Okay? 0, both of these have R number 1. Okay? R equals 0, R equals 1 for each of these. R equals 0, R equals 1 for this. Okay? So now you see, this time R equals 0. For these two, R equals 1. For this, R equals 2. Okay? And here, again, R equals 0, R equals 1, R equals 2. Any comments or questions about this?
Is the number of pivots just always going to be the same as the number of ones in the matrix?
Yes. Yes. But once you get to this reduced echelon form. So your colleague is suggesting, well, I did everything I could to reduce the matrix. And for instance, here I look at the number of ones. There's only one 1. And so the R number should be 1, 2. But maybe I should clarify this a little bit. You could also see 1, 1, 1, 0, 0, 0. Okay? Now the R number of this is not 3. It is again 1. So somehow this one is different than this one. Okay? When it comes to echelon forms, the fact that this entry, this leading entry is 1, is something important. Whereas these two are just numbers that I can anonymize. Okay? So, example, rank of 1, 1, 1, 0, 0, 0 is 1. Okay? Any comments or questions about this? What can I say about this R number and how it is related to M and N? Or maybe I should ask you, can I perhaps come up with certain inequalities or something for R? Yeah.
R is never going to be greater than the number of rows.
Say again?
R is never going to be greater than the
Okay.
number of rows.
Do we agree with this statement? Why? Because R is supposed to be the number of steps in my staircase. But if I have a 2 by 3 matrix, I'm never going to be able to get steps more than 2. At most, it can be 2. Okay? I'll write that later, because somehow it is also the case that you cannot have R greater than M. But that requires something. I'll mention that later. But somehow what your colleague ultimately suggests eventually is going to turn into what we're going to call the fundamental theorem of linear algebra. Okay? So this is like the one theorem that you keep using in this class. And we're just going to sort of see it once, twice, 3 times, and so on. And every time we see this theorem, we're going to add more sort of bells and whistles to it. Okay? Any other comments or questions about these reduced echelons? Now, how about echelons in general? Essentially, you take any reduced echelon and you mess it up just a little bit using row operations. The only thing you keep is the staircase shape. Okay? So for instance, if I start with a 1 by 1, you cannot do anything with this. So this stays. However, you can mess this up by turning this 1 into some number, anonymous, that is possibly not equal to 1. It cannot be 0, but any other number it can be. So that, remember, was how we denoted by this box. Just to remind you, star means some anonymous number that is possibly 0. Box means some number, some anonymous number that cannot be 0. So non-zero, star anonymous. Okay? Does this kind of make sense? Now, in practice, of course, it would probably go the other way around. In practice, probably you're not starting with a reduced echelon. You're starting with something that is more complicated. Eventually, you're going to reach to the echelon thing and then echelon step. And then you're going to do one more, probably, row reduction step to get from here to there. So for instance, if I were to have 1 by 2, again, I would have this. Okay? And so I look at this, for instance. This 0 is going to stay, you see. You cannot change this 0 by using row operations. But this 1, maybe you can mess it up. You can mess up. So this would turn into something like this. Or it could turn into something like this. Okay? Any comments or questions about this so far? Yeah.
form to the reduced echelon form is typically trivial. So why even the classification for reduced versus not?
Yeah, I mean, fair point. Technically, I'll put it this way. When I was first learning this stuff, I would just choose one of them. It's like, so I'm never gonna ask you, oh, turn this into a reduced echelon form. I'm just gonna say, probably I'm not even gonna ask you to turn it into an echelon form in the exam. Obviously, I need to ask you because it's in the textbook and you should know it and stuff like that. This is something people use. But what is the distinction between reduced echelon and echelon? Essentially, it's not that big of a deal as far as I'm concerned. Yeah. What is important still, though, is to be able to read off the R number. Okay? R number is important. Okay? Rank is important. Any other comments or questions? Now, let me ask you this. Why did I use this specific notation for this case? Box and a star. Why didn't I use box, box?
Because the one over there, has a star on it already, and the star can be a zero number, and the square cannot be zero, so you have to keep the star.
Exactly. So somehow, so for instance, when I say this, this means perhaps something like 2, 0. 2, 0 is in this form. No. 2, 5, let's say, is also in this form because star doesn't say you have to be using non-zero. Both of these are in echelon form. Okay? But if I were to say box, box, in a sense, this form promises more than you can actually accomplish. You actually don't have much to say about this entry here.
Because the only thing that cannot be is 0, 0.
Yeah. So you can't really promise much about this. That's why this is the appropriate notation.
Or any of them that have 0 in it.
Yeah, yeah.
It has to be all positive.
Okay. I'll do one more. Again, I suggest you think of these echelons as reduced echelon, but more messy. Let's do the complicated one, 2 by 3. Okay. So 0, 0, 0, 0, 0, 0. That's 1. I just look at this and I just mess it up just a little bit, right? Like this, or like so. Okay. Okay, like this. Just to be clear here. Then, so that's a star. That's a star. Then, like this. What is the correspondence? Of course, you just look at the same thing. I try to do the same sort of schematic here. take this, for instance, mess it up just a little bit. You see, if I use this to mess it up, I can just get rid of this 0. That's not a major issue. Return it here. But I told you what matters is that you keep the staircase, which means that, so how is the staircase defined? It's defined by the 0 entries underneath. So the zeros underneath the staircase you have to keep. Okay? Any comments or questions about any of this? Yeah.
So on the top, you changed like the zeros to stars. Are you allowed to do that?
Yes. So for instance, in this case, right? This compared to this. If I were to mess this up, I can just keep the staircase. I'm not going to touch these 3 zeros, but I can hide this 0 if I wanted.
Yeah, because okay, I see.
Yeah. And more to the point of what your colleague earlier suggested, as you see, the classification here pretty much duplicates the classification here. So this is essentially a matter of sort of personal style. Okay. Any other comments or questions about these? Okay. We did all this. So now we can start talking about vectors. Okay. What is a vector? Maybe I should ask you, what is a vector?
Line with direction.
You can think of it like that.
Something with direction and magnitude.
That's another way of saying it, yeah. Any other things?
A row of a matrix?
You can think of it like that, yes.
I was going to say it's the same thing in geometric form of a matrix.
Okay. So somehow these are all true. I would like to imagine, because I like calculus more than algebra stuff, I would like to imagine a vector to be something like a velocity. Or if you're a physicist, for instance, typically physicists say a vector is something that transforms like a vector. But then what does that mean? Okay, you sort of go into that. Physics people like to use these cryptic descriptions of things. I would suggest to you that ultimately, perhaps, one way to think about vectors is something that is possibly more complicated than a scalar. A scalar for us is going to be just one number. Okay? So, vectors. First, when you see scalar, this means just a single number. A vector for us is going to be something that is determined by possibly more than one number. So, something possibly more complicated than a scalar. Okay. Another thing that is very important for us is when people say, oh, that's a vector, you should really imagine, you can imagine sort of, you should imagine it like this. You can take like objects and you can pretty much add both of them together and scalar multiply. So, and scalar multiply. The complication is, so ultimately this part over here, vectors, matrices, and linear transformations, in a sense, these are interchangeable notions. Some of your colleagues already suggested, oh, a vector is a certain type of a matrix. But technically, it is also the case that a matrix is a certain type of a vector, and so on. This is where things start to get a little bit complicated. So in a sense, I would say vector is something that you imagine. Still, though, we have to start from somewhere. And here is the sort of standard way of first introducing a vector. This is going to be the sort of stable interpretation that's going to serve you well. So let's say here is this notation Rn. Okay. R to the n is the space. Okay, the space of all n-dimensional vectors. And for us, that means anything in the space is like this. So let's say v1, v2, dot, 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 vn, like so. Maybe I can write it like this. The collection of all such things, v1, v2, vn, are all real numbers. So technically what I'm saying is this n-dimensional vector, an n-dimensional vector is nothing but an n by 1 matrix. You can think of it like that too. Another way of writing the same thing that is very common. So tuple notation. Instead of writing it like this, you can just list the entries using commas and then put them in a parentheses. Like so. Okay. This is also very common. Warning. If I were to, instead of writing a tuple, if I were to write a 1 by n matrix without, so if I were to just drop the commas, it again has the same information, but that's a different object for us, okay? This 1 by n matrix is different from this n by 1 matrix. Okay, that's a different thing. So this is 1 by n. Is different. Next week, we're going to introduce something, an operation on matrices. This is what is called taking the transpose. And we're going to say this 1 by n is a transpose of this n by 1. I'll write it here. So you write this thing, and then you put a t to the top right corner. Some people use lowercase t, whatever. Sometimes you might see sort of like a dagger symbol or a star symbol, whatever, but these are all pretty much the same idea. You take your matrix, you flip it, okay? Rows become columns, columns become rows. Okay, so this is really where the geometry comes into play. This notation, this tuple notation, should remind you of this notation that we use, for instance, for points in the plane. X-axis, x-coordinate, y-coordinate. we likewise imagine vectors to be points in n-dimensional space. Okay? Let me check the time. Okay. So for instance, let's say I'm thinking of R2. Okay, this is the plane. And also the space of two-dimensional vectors, okay? So for instance, let's say V is 1, 0. Okay, I can write it like so. But using tuple notation, this is the same thing as this. Okay? And now I can draw the two axes. And typically when we sort of try to visualize things, the first entry here corresponds to the horizontal axis, and then the second entry corresponds to the y-axis. That's x. And so here is 1, 0. But like your colleagues suggested, instead of imagining this specific vector to be this point at 1, 0, I would rather you imagine it to be an arrow from the origin 0, 0 to this 1, 0. Okay? That's a better way of thinking of vectors. Okay? That's V. Okay? Let's do one more, perhaps W, 1, 1. Okay? Now this is the pair 1, 1. And this time, where is 1, 1? It's somewhere here perhaps. Okay? Again, I'm imagining this as an arrow. Okay? In terms of physics, you can think of V as unit motion in the horizontal axis, and W as slightly faster than unit motion in the diagonal. Well, we're going to try to make sense of these later. What is important at this stage for us is being able to understand these two things. That you can add and scalar multiply vectors. And how do you do this? You fix your dimension, okay? The shape has to be the same. You don't add a 5-dimensional vector to a 7-dimensional vector. Okay? You take two 5-dimensional vectors, let's say, and you add them up entry-wise. So this is what is called vector addition. So you take v1, v2, dot, 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 vn, plus, say, w1, w2, dot, 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 wn. The end result is going to be a vector of the same shape. Okay, so this is, for instance, n by 1. This too is an n by 1. You're going to end up with an n by 1. Entries are going to be v1 plus w1, v2 plus w2, all the way up to vn plus wn. That's how you vector add. You add entry-wise. So for instance, if I were to add these two things, 1, 0, plus 1, 1, 2, 1. Okay? Why do we do this? There are multiple reasons. One of them is somehow this addition, which is purely algebraic, as you can imagine, matches with the following intuition that comes from geometry. Namely, that you take the two arrows that correspond to the two vectors, and you put them consecutively, let's say. Here's what I'm trying to say. V plus W, for instance, corresponds to this. Go from the origin to 1, 0, that corresponds to V, and then use W to move from this endpoint. I'll draw it better. Okay. Okay. That's V. This is W. Take this, translate it over here, and adjoin it to the other one. Now you have a two-step motion from here to there and to there. And then the sum, algebraic sum here, corresponds to the arrow you end up getting here. Okay? How many of you have seen something like this before? Okay, pretty much all of you. Very good. Now the point of linear algebra, of course, is on the one hand that we have this connection between algebra and geometry, but also somehow, probably if you've seen something like this, you've seen like 2 dimensions or 3 dimensions. But certainly there's nothing stopping you from an algebraic point of view to consider like 55-dimensional spaces. It's harder perhaps to imagine there, but the same geometric intuition matches somehow with the algebra. And this is where things are going to get a little bit more abstract. Okay. Any comments or questions about this? The other operation here is scalar multiplication. For now, we're not multiplying vectors, okay? But we can multiply one vector with one scalar. Multiplication. So some constant, some scalar times v1, v2, dot, 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 vn is c times v1, c times v2, and so on. So for instance, if I were to look at minus v is nothing but minus 1 times v, of course. This is minus 1, 0. This scaling by a negative number corresponds to flipping this vector around the origin, meaning reflecting, I should say. So you take this, you reflect in the other direction. Okay? So this, if v is pointing this direction, minus v points in the exact opposite direction. Of course, I can do something like this as well. 2 times w is what? 2, 2. Geometrically then, scalar multiplying a vector by a constant corresponds to stretching it or contracting it by that factor. If I take this w and scalar multiply it by 2, now I just take the vector, stretch it, okay? because 2 is larger than 1. Okay. So this is all there is to it. Addition and scalar multiplication. These two things are the main operations that we end up doing. Any comments or questions about any of this? Okay. Now perhaps let's try to be a little bit more intuitive. When we see something like this, let me think. Before writing, I'll just say it like this. I wrote here, for instance, vectors are things that are possibly more complicated than a scalar. Now, in principle, for instance, in this definition, there's nothing stopping you from picking n equals 1. So real numbers themselves, the line itself, is supposed to be a space of, or the space of one-dimensional vectors. Okay? And certainly you can add two numbers, and you can scalar one number by another one. Addition, I think, is somewhat more intuitive in this context. Example. R is the same thing as r to the 1, of course. Okay. So when I write, for instance, something like 1 plus 2 equals 3, okay, this is the standard addition, of course, but I can also imagine it to be vector addition. Scalars are vectors, in principle. The intuitive way of thinking about this equation would be something like this. If I take a rod of length 1 unit, and next to it I put another rod of 2 units length, then ultimately the totality would be a rod of length 3. Okay. Ancient Greek people would sort of make sense of this equation using sort of physical things, for instance. If I were to do 2 times 3, I get 6. The question is how to imagine this 2 times 3 equals 6 equation from an intuitive point of view. Any guesses?
Take 2 rods of length 3 and add them together, essentially.
But how do you get 6?
If you add, I guess the idea is, since you have 2 rods of length 3, you have from 0 to 3, and then from 3 to 6.
Okay. So that's one way of thinking about it. This really stands for, you can say, this. Take two rods, both of length 3, and that gives you 6. You can think of it like this. The one way to not think about it is to say, 2 times 3 is 6, and 6 is the area. Okay? So some of you probably know something about dimensional analysis. If I'm trying to really imagine this in the context of linear algebra, maybe I should use this thing. If 3 is the vector, and if this is the scalar, this should be, again, a vector, okay, of the same type. And so this would be the appropriate way of thinking about this equation, but not this. Okay? 2 times 3 is 6. This equation also represents this, but this is not scalar multiplication. In other words, the scalar that we're using okay, when we're doing scalar multiplication, you should imagine as a dimensionless number. It's a dimensionless number. It doesn't have any SI units associated with it. Okay. That's it for today. We'll continue tomorrow. Thank you. All right, let's start. Good morning. So today we're going to switch over to these notions: linear combination, linear span, and linear independence. This is where we're going to sort of have a spike in complexity, is what I'm speculating, that I'm expecting. Unfortunately, this is like these two matters, especially span and independence. I would guess that it's going to take pretty much the whole course for you to get accustomed to these ideas. I need to introduce something called set notation because they use it in the textbook. It's also useful for math purposes, of course, but I need to introduce it. And even before that, I wanted to mention this theorem. It basically says any matrix, once you fix the matrix, you row reduce it, you get to a unique echelon form or a unique reduced echelon form. I stated this a couple times already in class. I said, oh, you just start with something and you sort of reduce it, and you eventually end up at exactly one of the forms that we list. Now, in the textbook, they state theorems like this, and some of them have proofs and stuff like that. This is not a proof-based course, and I'm not going to be proving anything, okay? And I'm not going to ask you to be able to prove things also, okay? Still, though, perhaps an important matter is being able to justify. Certainly, you're responsible for the contents of these theorems that you're going to see. And I might mention why a certain statement should be true. In this case, I don't think too much to be said. Just based on experience, I think you would argue, you would agree with me that you would reduce any matrix to a unique form. But there's going to be more complicated theorems in the future. One of them is what is called the singular value decomposition, for instance. That's kind of a, that's complicated in a sense. Spectral theorem, that's complicated. There's a bunch of other theorems like this. I'm going to, again, not prove them exactly, but I might give some idea, some sort of abstract-looking justification as to why it should be true. But like I said, this is not a proof-based course. I'm not going to be giving proofs in the class. Okay. If you want to sort of read it out, it's perfectly fine. I mean, part of it is that most of the alleged proofs in the textbook I would call a calculation, really. There's nothing sort of scary going on, and the textbook typically sort of avoids the types of proofs that are actually kind of mathy. Okay, so vector space. We talked about this. Really what you should keep in mind is whenever someone calls, oh, this is a vector, whatever, really what they're talking about is that this thing, this object, is in a collection of like things, and you get to add and scalar multiply. That's what you should think of. So you should think of vectors and vector spaces and so on in terms of what you can do and how we can combine them. So whenever you see vector space, abstractly, you should think of as, oh, it's a bunch of things I can add. Maybe I should say I can vector add. And scalar multiply. Okay? And if you need sort of an instantiation of a vector space, when people are talking about vectors, the first thing you should think of is Rn, okay? I'll write it here. Rn is the first example. For any n, for n equals 1 to whatever, technically also 0, but r to the 0, let's not worry about that. R to the 1, R to the 2, whatever, these are all the standard examples of vectors. And when someone talks about an n-dimensional vector, you should think of r to the n. 1D means r, 2D means r2, and so on. Okay, that's your first interpretation of this word. But then, technically speaking, you can take a collection of matrices as well, m by n matrices, let's say. Just like you can add and scalar multiply n by 1 matrices, vectors. You can do the same thing with m by n's. Again, do the same stuff entry-wise. So I'll write it here. I'll write it here. I'm going to denote this by curly m by n, semicolon r, all m by n matrices. This is also a vector space technically, so matrices are also technically vectors. And how do you add a scalar multiply? Let's just record again. You always use the same rule, okay? So vector add a11 dot 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 a1n, and then a m1 dot 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 a mn. Take one m by n and add it to another m by n, entry-wise. Okay. M, N, P, M, N. That's how you add two matrices. Pretty much exactly the same way you would add vectors in Rn. Right, so here we said, for instance, x1 dot 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 xn added to y1 dot 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 yn. How do you do it? Well, you just look at the corresponding entries and add them up. x1 plus y1 is the first entry of the sum, and so on. And then xn plus yn is the last entry. It's the same idea. Okay? There's no difference in how you execute these. And likewise, we talked about how to scalar multiply c times x1 dot 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 xn. How do you do this? Well, you just distribute c, right? Distribute c over all the entries. cx1 dot 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 cxn. How do you do this with matrices? You again do the same thing. Distribute over all entries. Oh, that should be 1n. m1 dot 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 a mn. Take that c, that's a constant, that's a scalar, distribute over all the entries. C times a11 dot dot dot, c times a1n, and then c times a m1 dot dot dot, c times a mn. Okay. Now, this is where things get complicated. If a certain problem really requires you to think of matrices, rectangular matrices like this, as vectors themselves, I'm going to explicitly state, take this vector space of matrices. That means, oh, this is a set of matrices that say 2 by 3, but I want you to think of them as vectors, okay? This is just some logistical matter, not super important. Any questions about this? Yeah, go ahead.
Can you explain that notation, the curly m?
Yeah, I'm just recording this. These are the dimensions, and this is the entries. Matrices of dimension m by n, where my entries are coming from reals.
So is that a function?
No.
Like, I think I'm very lost on what it is.
Yeah, because I'm like, what's the symbol in between the N and the R?
Semicolon.
Okay.
Yes. You can call it a functor, but let's not go there.
Okay.
Yeah, go ahead.
What if you try and add matrices that have different m's and n's?
We don't do that. For now, we don't do that. What you could do is you could take the smaller one, pad it out. That's what you would do. Add a bunch of zeros so that the dimensions are matched, and then you would add them together. If they are in different dimensions, you don't add things, okay? At least for now. Okay. You would also see notation like this. M by n, r. There's also notation like this. You would also see r to the m by n. They do this as well. These are all sort of common notations. The reason why I don't like using this notation is because somehow r to the 2 times 3, this should be the space of 2 by 3 matrices. I would like to think of it as a different thing than the space of 6-dimensional vectors. R to the 6 should be different from the space of 2 by 3 matrices. So the difference between the two of them is, in computer science, what is called the vectorization. You take an array and you vectorize or flatten or reshape, whatever. There's a bunch of names, but it turns out that it's good practice to separate these two types of vector spaces for now. Okay. Okay, set notation. So this is something they use in the textbook. You'll see these curly braces, okay? So whenever you see something like this, let's say A, B, C, and then curly braces, that's an example. This basically means it's an unordered list. Now, we had the brackets that they use in the textbook, or instead of that, I'm using parentheses like this. These are ordered, okay? The order matters here. If you see this notation, the order does not matter. That's the difference. Okay, so this is the same thing as BAC, for instance. So that's a set or unordered list. Okay, I kind of used the notation yesterday when I was talking about this Rn as well. Okay, this is just some notation. Let's now switch over to these three ideas: linear combination, linear span, linear independence. Now, I introduced this space of matrices, but obviously I'm not going to think about them for now. It's going to come in handy next week and going forward. So for the rest of this week, we're just looking at Rn. Okay. Now, I told you in a vector space in Rn, the two things you can do is vector add and scalar multiply. If you do this a bunch of times, that's what you get. That's when you get a linear combination. So you don't need to necessarily add two of the vectors. You can add a bunch of them. Finitely many, of course. I'll write it here. So let B1 dot 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 Bn, maybe I should say Bp, be vectors in Rn. Okay. So each of these is an n-tuple. I have in total n times p many numbers now. Fix them, okay? And C1 dot 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 Cp be real numbers, be scalars, better, scalars. then what I'm going to do is I'm going to take vi, scale it by ci. Again, I have p many vectors. Then add all of them up. That's what is called a linear combination. Combo is c1 times v1 plus c2 times v2 plus dot 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 plus cp times vp. Okay. We just do vector addition and scalar multiplication multiple times. So ultimately, this again, let me reiterate, is an n-dimensional vector. When you take a linear combination of n-dimensional vectors, you get back possibly a different n-dimensional vector. Again in Rn. Now, one thing you can do if you don't want to sort of keep writing this all the time, you can use this summation notation. This is basically a for loop, okay? Instead of writing it like this, you use this capital sigma, okay? And then you index in, let's say I, from 1 to p, ci, vi. If you want to be fast, instead of writing it like this, you can write it like this as well. How many of you have seen this notation before? Okay, most of you. Okay. Again, to reiterate, what does this mean? This means look at ci, vi, and add all such terms where I runs from 1 to p. It's a for loop. Okay? In physics, for instance, they don't even write this sigma notation. They have what is called the Einstein notation. They sort of do some stuff with indices and stuff like that, but we're not going to use it. This is fairly common. We're just going to keep to that. Okay, so here's an example, for instance. I don't need this. Just delete this much for now. Example. So for instance, what we can say is this. Any 3D vector, so vector in R3, okay, is a linear combination of the following. Is a linear combo of the following three vectors. E1 I'm going to denote by 1, 0, 0. E2 to be 0, 1, 0. E3 to be 0, 0, 1. Okay. Why is that? Well, let's just take some three-dimensional vector, x, y, z. Okay. This is where perhaps things get a little bit complicated, because even though we're technically talking about addition, you can also go backwards as well. If you have a vector like this, you can split it into some ends. So what I'm going to do, for instance, here, I can say, oh, x, y, z is the sum of x, 0, 0 plus 0, y, z. I can do that, for instance. Does this make sense? Okay. There's nothing stopping me from, splitting this further. Okay. Split the vector additions. And likewise, I can just factor out common scalars. But in this case, for instance, I can say this is nothing but x times 1, 0, 0. x is a number, I can take it out. Okay? And likewise, I can take the y out as a constant, as a scalar, take the z out. X, y, z are constants here, they are scalars. I was able to write an arbitrary vector in 3 dimensions as, you see, a linear combination of the standard directions. So if you want, I can write it like so. X, E1 plus Y, E2 plus Z, E3. Okay. So for instance, if you've taken multivariable calculus and stuff, instead of E1, E2, E3, you would use like I hat and whatever. It's the same thing. So I hat, J hat, K hat. Okay. This is a calculus notation. In linear algebra, we typically use this E1, E2, E3, whatever. How can I visualize this? Well, 3 dimensions I can imagine as the XYZ space. Okay, that's X, that's Y, that's Z. Let's remember how we were visualizing these vectors. So 1, 0, 0 is a point here. It's on the x-axis. But instead of thinking of the point, I'm imagining the arrow from the origin to this point as this vector. Okay? So when I'm trying to visualize E1, I'm really thinking of this vector. This is E1, or in calculus notation, I hat, or I bar, whatever. Okay? This guy then becomes the vector in the y direction, and then E3 becomes the vector in the z direction. Comments or questions about this? Now here's a different interpretation of this linear combination from, say, robotics or control theory. Linear combinations are all about, and eventually that's going to turn into this linear span as well. These two are somewhat related. Linear combinations are all about accessibility, where you can go. You say to yourself, if I'm taking the linear combinations of these 3 specific vectors, you say, I allow myself to move in specifically these 3 directions. And you say, where else can I reach? Starting from the origin. Okay? That's the control theory interpretation of what is happening here. So for instance, another example, again in 3 dimensions. Let's do 4 dimensions this time, perhaps, to make it different a little bit. E1 is again 1, 0, 0, 0. E2 is 0, 1, 0, 0. Now let's say I'm taking a linear combination of these 2 vectors. Actually, let's use the third one as well. E3, 0, 0, 1, 0. Okay. Now, thinking of this control theory interpretation, my ambient space has 4 dimensions, okay? And when I think about a linear combination, an arbitrary linear combination of these 3 vectors, I'm really looking at the part of this 4-dimensional space that I can reach using motion in any one of these directions consecutively, but starting from the origin. Okay? And so let's use the set notation as well. So you can write it like this. So this is a set of vectors, for instance. These are allowed directions. Allowed directions, a linear combination of these is all the positions you can reach using motion only in one of these three directions. But you can sort of like mix and match. Combo is a place you can reach by motion in these directions. Starting from the origin. What is the origin? It's the vector with all zeros. Starting from the origin. And so 0, 0, 0, 0. You'll also see the notation just 1, 0. Okay? We just overload this 0. This means the vector 0, whatever the 0 is in the context. Okay. And so, for instance, I could ask you, can I write 1, 1, 1, 1 as a linear combination of these three vectors? You can't. Okay? Why? Because somehow in this vector, so this, imagine, represents a four-dimensional position. Your fourth direction has magnitude 1. But by taking linear combinations of these three, look at the fourth entry. None of these directions allow you to move in the fourth direction. Okay? Cannot be written as a linear combo of the set of the given vectors. Okay? Another way to say this would be to say, well, this specific vector is not accessible using these three. Inaccessible, not accessible. Okay. Go ahead. Oh, question. Now, the collection of all those vectors that are accessible given a set of vectors is what is defined as the span of these vectors. So, span of v1 dot 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 vp, okay. In the textbook, I think they use the curly braces here. Doesn't really matter. Span of these is the collection of all linear combos. Okay. All linear combos of v1 to vp. So linear combinations and spans are all about accessibility, where you can reach from the origin. I'll give one more example. Again, let's stick to 3 dimensions. R3, okay? Let's say S is the set of vectors Again, E1, let's say 1, 0, 0, same thing. E2 is the 0, 1, 0 vector. And then let's say E3 is E1 plus E2. If I want to be more explicit, I can think of it as 1, 1, 0, of course. I can just add. Okay. Again, I have 3 vectors. I'm in 3 dimensions, and I have 3 vectors. I can visualize this like so. X, Y, Z. E1, E2, and how can I visualize E3? Well, I'm just going to adjoin one of these vectors next to the other one. And this right here is E3. Okay? Now, what is the span of this set S? Okay, any other guesses? Maybe you can say a couple words about why that should be the answer.
I mean, so obviously the span is just defined by all linear combos you can make, which limit the linear combos. You have no way to, I guess, change what your third, I guess, like dimension of each of these vectors are. So you really only be able to edit these first like 2 entries in a given vector, and so that space is not going to be able to have that third dimension at all when you're looking at it geometrically. It's just going to be in this 2 dimensions because that's the only like degrees of freedom you really have is the first and second.
Very good. Does this make sense? So in a sense, E1 doesn't allow you to do anything with the third direction. You won't be able to elevate yourself. Likewise, E2 and likewise E3. Okay? So you're stuck in the xy plane. This is the xy plane. Well, I guess the problem here, of course, is that I'm specifically looking at examples where the numbers are straightforward. But the problem now that we need to deal with is the issue of perhaps having different sets of vectors where maybe, again, the span is a plane, but it's not one of these nice planes. Maybe it's sort of like skewed like this. Now, geometry is going to be harder to visualize. Okay? But of course, that's where we start using algebra. And it all boils down to solving systems of equations. Okay? We'll do a more complicated example in a second. I want to say one more thing. In this case, for instance, E3 is somewhat redundant. If I have E1 and E2, I don't need to say explicitly, oh, I'm allowing my robot to go in the E3 direction also. Because any motion in the E3 direction, I can split into motion in the E1 direction and the E2 direction. So this is redundant, really. But that's OK. Redundancy is a different matter. Spans and linear combinations are all about accessibility, where we can go. Redundancy, or non-redundancy, is going to be about this linear independence that we're going to discuss in a second. OK? Let me write it here again. So this is about accessibility. This is about non-redundancy. If you have independence, that means that your set is not redundant. So there is no sort of redundant vectors. We'll say more about this in a second. Before that, I want to do a more complicated example. This is the intuition, OK? But somehow, being able to answer, oh, can I go to this position using this specific set of vectors, ends up being somewhat more somewhat harder to visualize if your vectors, if the vectors given, are more complicated. Okay. So here's the example. Again, we're in 3 dimensions. 3D. So let's say my set is A1. The first vector is 1, -2, -5. And then my second vector, A2, is 2, 5, 6. And the question is, and I have this other vector, the target, 7, 4, -3. The question is, can I access B using linear combinations of A1 and A2? In other words, is B in the span of A1, A2? Question, is B in span of S? Now, how do you figure that out? Okay. Well, you use the power of algebra. Just write down the definition. So, C1, let's do it like this. This is sort of like in general English. Let's try to rephrase the question in more actionable terms. Opening up the definition, this ultimately boils down to the following mathematical question, i.e., so that is, are there 2 scalars, C1, C2, such that if I were to use these 2 numbers to take the linear combination of A1 and A2, I get B. Such that C1A1 plus C2A2 equals B. Okay. Any comments about this so far? So this is really what I'm going to focus on. And here's where we're going to start feeling the power of matrix manipulations. So B equals 7, 4, -3. And how do you come up with something like this? You say, oh, let's suppose that there's a C1 and C2, and try to do some manipulations with this equations and see where it takes us. C1, instead of A1, of course, I'm going to write this now, plus C2 times this other one. Okay? Just substitute it. Now what I can do is, I can scalar multiply. It's a scalar, distribute, scalar, distribute, and then add everything to consolidate to have exactly 1 vector on the right-hand side. So then this becomes this. A C1 plus 2C2 minus 2C1 plus 5C2 minus 5C1 plus 6C2. Okay. Now, when do I get to say 2 vectors are the same? In other words, when is this vector the same thing as this vector? That happens exactly when the corresponding entries are the same. So 7 equals whatever this is. 4 equals whatever this is, and minus 3 equals whatever this is. Turn this then into a system of equations. Okay? So C1 plus 2C2 equals 7, minus 2C1 plus 5C2 equals 4, and then minus 5C1 plus 6C2 equals minus 3. Okay? I'm just doing this once, but ultimately this is an important matter. In other words, we have all these like bombastic sort of phrases and all that stuff, but when you open things up, ultimately this question is just a more complicated way of asking, solve this system. Okay? So how do you solve the system? You solve it exactly the way we learned in week 1. And so one thing I can do is I can turn this into an augmented matrix. This is a system with 3 equations with 2 unknowns. Okay, so 1, 2, 7, minus 2, 5, 4, minus 5, 6, minus 3. This is augmented matrix I need to be focusing on. Okay. Does this make sense? Now, I did this step by step, but you can just fast forward this. You can just say, well, when they ask me something like this, all I need to do is take A1, put it in the first column, take A2, put it in the second column, put the bar, take B, put it in the third column. That's the augmented matrix I should be focusing on. You can say that too. Okay. Now, this is one of the reasons why I'm not going to spend this much time on theorems in the textbook. There's a bunch of theorems in the textbook that basically says, oh, you can do this and that, and if you do this, it solves. But as far as I'm concerned, it's much easier to just go through things a couple times to know by heart instead of memorizing the statement of the theorem, because a lot of the theorems in the textbook, frankly, are just like nothing burgers. Okay, just run the matrix manipulation business. It's going to tell you what the theorem actually tells you you're able to do. Okay, so to reiterate, what I said was either you can just open up the definition and manipulate things to get the augmented matrix, or if you want to fast forward, if they ask you, oh, I give you a bunch of vectors and I'm asking, is this vector in the span? Just take these vectors, okay, put them on the left-hand side of your augmented matrix. Take your other vector that is the target where you're trying to reach. Put it on the right-hand side. Reduce this. That's going to give you the solutions associated are going to give you the answer. Any comments about this so far? Okay. Okay, they do it in the textbook. Should we solve this system again? Just a review. If you want to, I can just solve it. It says, for instance, x1 is, or rather c1 is 3 and c2 is 2 here. Solve exactly as we did in the previous week. Okay, yeah, go ahead.
So I could check if I got 3 and 2. I could check my answer by plugging 3 in for C1 and 2 in for C2 and making sure that that equals B.
Yes. So just let's, I'll leave this to you if you want. It's in the textbook. Let's do instead what your colleague is suggesting. Just like you can check whether or not certain numbers are really the solution, you just plug it in. In this case, what does plugging it in mean? Well, you just take 3 times a1, 2 times a2, and that linear combination should equal this. Let's just do that then. I'll do it here. Check. So C1, A1 plus C2, A2 is what? So I'm just going to plug in everything. So this is 3, 1 minus 2 minus 5, plus 2, 2, 5, 6. Okay, so scalar multiply, 3 minus 6 minus 15. I just distributed this 3 over the entries, plus 4, 10, 12. Likewise, I distributed this 2 over the entries, and then now I'm going to add the matching terms. That's 7, 4, minus 3. That's exactly B. Okay, good. Go ahead.
So what would we say here? Would we just say yes?
Yes. The answer is yes. B is in the span of S.
And then let's say we did all this work and we found out that it was inconsistent, then the answer would be no.
Exactly. Yes.
For that type of matrix, if you solve it out, one of those numbers at the end should be 0, right? Or would they all have a number as a result? Because you said like C1 is 3 and C2 is 2, but there's 3 numbers right there.
There are 2 variables though.
But how would that like work? Like what would the matrix turn out to be?
You would have a 0, 0, 0. Very good.
Okay.
Yeah.
Yeah, because you said that one was kind of like no solution, so.
I didn't say that. What I said was, if on the left-hand side you have 0, zeros, and on the right-hand side you're going to have a non-zero, I guarantee you, if you're able to, and you are able to, if you're able to reduce one of these rows on the left-hand side to a 0, on the right-hand side, I guarantee you it's going to be 0.
Okay. Yeah, I can see.
Yes. Any other comments or questions? Now, okay, in the definition of spans, linear combinations, I'm not saying anything about non-redundancy, okay? So I could have had something like this too and stuff. So when you switch over to the system, B would be in the span if and only if you can at least find one solution. You don't care at this stage if you have a unique solution. That would be about this, okay? That would be about non-redundancy. If you have multiple solutions in this case, that would mean that your set has some redundant vectors. But that's about the other part. That's about this linear independence. Span is all about whether or not you can go there. Doesn't say anything about you can go there uniquely. Okay? That's the other side. And somehow we're going to mix these two things, span plus independence, and that's going to give us what is called the basis. Okay? So these are sort of the two sides of the equation in a sense. They sort of balance each other out. Any comments or questions about this? Again, I didn't do this calculation over here. It's in the textbook. You can have a look. Nothing new, okay? It's the same stuff. Okay, we can stop here. We're going to continue on Friday. Thank you. All right, let's start. Good morning. So today we have a couple of things to define. Talk about we had talked about this linear combination, linear span business. I'm going to remind you what this means in a second. I'm going to try to sort of collect all different ways of writing pretty much the same thing in a second. Then we're going to switch over to this linear independence and dependence business. So what was our intuition? The intuition is, well, linear combinations and linear spans are all about this accessibility business, right? So you start at the origin, whatever your origin is, given your vector space, and then you have a bunch of vectors, and then you're allowed to move only in these directions that your vectors tell you. And then you're asking, where else can I reach? So these are about accessibility. This is sort of the other side of the medallion in a sense. Independence is when you have no redundant vectors, and its opposite, that's kind of confusing, but dependence is when you have redundant vectors. Okay? So this independence, non-redundancy. And then we'll talk about this linear transformation business. Problem set 1 is due tonight. Problem set 2 is almost ready. I'm going to release it later today. So some of you had technical issues with submitting the problem sets. If you end up not being able to sort of submit, let's say by 11 p.m. today, you probably should be sending your PDF file to me, or whatever, your submission, your work, so that I know that you have actually done something. And hopefully we'll figure out how to mitigate those issues, technical matters, and all that. Are there any questions before I start? So here's the recap, okay? This is just this abstract stuff. I'm just going to focus on how we write things. We started with this system notation. We said, oh, we have a11x1 plus dot 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 plus a1n xn equals b1. And then we had am1x1 plus dot 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 plus amn xn equals bm. This was how we started. We looked at specific cases of this, but this is a general system. Here, aij's are given numbers typically, and bj's are also given numbers, or maybe I should say bi's. And then you're trying to solve for xj's. And so this is a system notation. And then we said, oh, we can write this in two other ways. The first way was this matrix form. What we said was, well, just sort of factor out all the unknowns and put them in one matrix, like so. And then right-hand side, again, compile all of them into one matrix or vector, whatever you want to call, like so. Okay. And then we said, well, you can look at the remaining numbers on the left-hand side, put them in one m by n also. Okay. This was the matrix form of the same thing. Or in the textbook, they also say this is the matrix equation or whatever. And what we can do is we can say, oh, this guy I'm going to call x. This guy I'm going to call b. And this let's call capital A. Just to store everything, simplify. So instead of using these indices and stuff like that, if you want to be fast, you can write the same thing as ax equals b also. We haven't actually used this so far, this notation, but it's still useful. Let me also say one thing. One of the things we said was, well, given any matrix, we have the number of rows and number of columns. And I told you always, so the first number, first integer, is always the number of rows. When they say m by n, m is the number of rows, n is the number of columns. And so for instance, what we said is, to denote that this A matrix is m by n, I'm going to use m and n as subscripts. M is going to go to the left, n is going to go to the right. Okay? But I can do the same thing with the x matrix or vector. X is n by 1. Okay? And so when I put these two together, I get m by 1. Okay? What does this mean? This means if you put two matrices together, this is going to be well defined for us. Okay? Insofar as this number in the middle is the same, in which case when we put them together, this is going to cancel out, and we're going to end up with the sort of this dimension and this dimension. So somehow this heuristic ends up being very useful when it comes to dimension counts and stuff like that, or if you can actually multiply two things. We're going to talk all about these matrix multiplication business next week, but already sort of we're going toward there. And in fact, what we're going to say, or let me perhaps back up a little bit. One of the things I told you is, well, again, just like with matrices, with systems too, we have two important numbers: number of equations, number of unknowns. Number of equations is m. I have m equations. Number of unknowns is n. I have n unknowns. Okay? And I also told you m is the dimension of the output space. I just like state it this way. And I said n is the dimension of the input space. Okay? Let's remind ourselves. Number of equations, dim of output, and if I want to think of it as A as well, it's the number of rows also. Okay? N, on the other hand, is the number of unknowns, which is the dimension of inputs, which is the same thing as number of columns. Okay? Are we happy so far? This is nothing new. I had mentioned all this before. I'm just recapping sort of all different ways of basically saying the same thing in multiple ways. Okay? Let's keep going. So I guess maybe just to match this with this, at the end of today, when we start thinking about linear transformations, we're going to try to make sense of this A as a thing in and of itself. We would like to think of A as a linear transformation from n dimensions to m dimensions. Okay, that's going to be the third interpretation that we're going to use. We'll get there, though. Comments or questions there? Go ahead.
Is that x in the top right of the, yeah, right there, it's the x1.
x1?
In the top, on the right side.
xn?
Is this supposed to be xn?
Yes. X sub n. Nth unknown. Okay. So the usage of this notation, the matrix form, and this more sort of compressed matrix form, it's going to come in handy starting from this linear transformation interpretation and next week. What else did we did? So maybe I can call this also matrix form. Of course, the more important thing that we were using so far is the so-called augmented matrix form. What did we do there? Well, we basically got rid of this middle part and sort of collapsed these two parts into one. And so we wrote a11 dot 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 a1n bar b1 dot 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 am1 dot 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 amn like this. And this is the augmented matrix form. Okay. We did a bunch of like row reduction and stuff like that to get the solutions of ultimately this. And just like I compressed this into letters, single letters, I can compress this as well, and I can write it a bar lowercase b. We can write it like this as well. Again, augmented matrix. Another thing that we kind of mentioned, we're going to talk about it later more, is, well, instead of thinking of this augmented matrix as m by n plus 1, I can think of it as 1 by 2 with matrix entries. This is the idea of this blocking or partitioning. Blocked, let's say, or partitioned. Okay, we're going to talk about that later more. This was basically the content of week 1. Now I want to incorporate the notion of linear span and linear combinations into this as well. Okay, because somehow, remember on Wednesday we had this example of, oh, here are a bunch of vectors, and they give you yet another vector, and they ask you, is this new vector a linear combination of the other ones? And we realized it ultimately boils down to this augmented matrix. You solve it, find numbers, and so on. So somehow, even though it may not look like it, the matter of linear spans ultimately end up being about solving systems of equations as well. So what's going to happen is our main sort of computational tool is going to be this row reduction of augmented matrices and so on. And your job is going to be, oh, here's this more complicated way of asking whatever. You're going to try to sort of reduce that complicated question to basically solving a system of equations. Okay? That's going to be the main goal for a while. And in fact, throughout this course. So, instead of going from here to there, what I'm going to do is this. Okay, I'm going to say, well, I can think of this as one entry. It's ultimately a real number. It's a number. The second row as a number. The mth row as a number on the left-hand side. So here's yet another way of writing the same thing. Okay. And in fact, I'll start with the right-hand side. Okay. I'm going to write it like so. A11 x1 plus dot 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 plus A1n xn. AM1 x1 plus dot 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 plus AMN xn. Okay. So just like here, so this is one way of using matrices in this case to represent this, but there are multiple ways of representing the same thing. This time I decided to represent the same system of equations this way. Vector equals vector, I can say that. So, and to reiterate, when I write it like this, I really mean the right-hand side too is an m by 1, okay? It's an m by 1. One column everywhere, so it's a vector. And then we said, oh, if you have vectors of the same type, we can add them, vector add them, or scalar multiply them. And of course, we can do the same things backwards. In other words, we can sort of split a complicated vector like this into a bunch of sums. And then we can take out certain constants if you want it. I'll do this step by step this time. So this is the same thing as this. Okay. Maybe I'll write the second one as well. A12 x1, x2 rather. Dot dot dot. A m2 x2 plus dot 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 plus A1, what was it? N xn dot 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 A mn xn. Okay, I just rewound vector addition. Instead of going from here to there, I can go backwards. But then, for instance, if I focus on this m by 1, again to reiterate, all of these are m by 1s. Okay. I see, for instance, in the first one, x1, even though it's an unknown, ultimately it's going to be a number, so it's a scalar. I can take it out as a scalar. Likewise here, I can take out x2. Here I can take out xn. And I can write it like this. Mn. Any questions or comments so far? Now, what is the significance of writing the same thing this way? Well, on Wednesday we talked about how this right-hand side is a linear combination of the vectors that are the columns of A. Okay? I'll use a different color. Linear combo of columns of A. Okay? See, for instance, this guy is precisely the first column of A, and so on. This right here is the nth column of A. I had n columns in A, and here I'm taking the linear combination of n vectors, but they're all in m dimensions. Okay? This is where things start to get kind of complicated. Any comments or questions? So then what I can say is this, okay? With systems, when you see a system, what we were trying to do was to solve it. There were two cases. A system is either consistent, has at least one solution, maybe infinitely many, but at least one, or it has no solution, right? These are the only two options. If the system is if it has a solution, we just said consistent. If the system has no solution, we called it inconsistent. Okay? But then, as this system is equivalent to saying that this right-hand side vector, B, is a linear combination of columns of A, I can sort of rephrase the consistency of the system in terms of linear spans. What I can say is this. System is consistent if and only if the B vector is a linear combination of columns of A, if and only if the B vector is in the span of the columns of A. This is just like wordplay, but this is part of linear algebra. This you're going to have to get used to, okay? I'll write it down because this is important. Maybe I'll write it here. This is important. So let's use a red star over here. Star is consistent, has a solution, right? This is the same thing as saying that B, the right-hand side vector, is a linear combination of columns of A. B is a linear combo of columns of A. But if I want to use the notion of a span, I can just say B is in the span of the columns of A. span of columns of A. These are all the same thing, okay? Any comments or questions about this?
So a linear combination is just when we are multiplying by a scalar, right? So
Multiply a bunch of scalars, add them up. So you can do, at this stage, you can only do two things with vectors. Scalar multiply, vector add. If you do a bunch of these, that's a linear combination.
so we've only been doing linear combinations.
Yes. So you could also say, for instance, a scalar multiplication is also a specific type of a linear combination. It's kind of like a degenerate case, if you want. Or a vector addition is a specific type of a linear combination. Any comments or questions about this? Now, this you need to know, okay? I'm not going to tell you in the exam or whatever. I'm just going to tell you, like, is this in the span? I'm going to use these like more higher order interpretations of what is happening. You need to be able to know, you need to be able to sort of say, oh, this means this, and like, this is like, just like solving the system, whatever. That's going to be your job. Transitioning between interpretations of what is actually being asked. Okay, so this is linear span, linear combination business, okay? Using vector addition, it's pretty much the same thing as writing a system. Somehow, linear independence too ultimately ends up being writing systems, but it's, I would presume, slightly harder to grasp, okay? It's somewhat more convoluted as far as I'm concerned. Again, I'm going to take a linear combination, okay? I have like p vectors in n dimensions, take a bunch of scalars again. I look at this set of vectors. Remember, this was a set notation. Doesn't matter in which order I write these. And I'm going to call it linearly independent if all the scalars are 0, then the linear combination is also 0. But of course, you should remember, this 0 is the number 0, this 0 is the vector 0. Because v1, v2, whatever, these are all vectors. When you add vectors, you're going to get a vector. It's a vector. So this is a 0 in Rn. Okay. This is the n by 1 0 vector. Any comments or questions? I'll do an example in a second. So this is the thing you need to figure out for linear independence. The problem, of course, is that this actually doesn't say anything. I'm saying if all the constants are 0, well, on the left-hand side, I'm going to have a 0 no matter what vi's are. This is like a dumb statement. Doesn't say anything. Okay? This is where things get complicated. I wrote it wrong. It's the other way around. It's this way. Okay? This is the right way. The other way around, it always works. If your scalars are 0, well, if you scale a vector by 0, you're going to get 0. Left-hand side would be 0. Linear independence is going backwards. You take a linear combination, somehow it gives you the 0 vector. From that, somehow, you need to deduce that your constants have to be 0, your scalars have to be 0. From a control theory point of view, we can interpret this like this, okay? So remember, a linear combination is all about moving. You start at the origin, and these are your valid directions. You move around in your space. What this says is, If you end up at the origin again, so somehow you moved around and you looped back to the origin, you actually never moved. That's the interpretation. Here's an example. Somehow this condition is the condition that captures this non-redundancy. Let's start simple. Let's say we're in 2 dimensions. Okay, plane. Let's take, for instance, let's say my set of vectors is, well, I guess I don't need to use this letter here actually for now. Let's just use this. Let's say v1 is 1, 0. Maybe I should say e1. e2 is 0, 1. And then let's say the third vector is e1 plus e2. And what is the numerical value of this? Well, you just take these 2 vectors and add them entry-wise. This by this is 1. This by this is 1 again. So this is nothing but 1, 1. Okay. We had looked into a very similar set on Wednesday when it came to spans. We pretty much did the same thing, but in 3 dimensions. Let's just look at this one. So let's remember how to visualize vectors in this case. Well, I'm just thinking of this as the tuple, right? So this is 1, 0, this is 0, 1, this is 1, 1. This is 0, 1. This is 1, 1. And then I can plot these like so. X, Y, like this perhaps. Now, 1, 0 is this point. But remember, we don't want to think of vectors as points. Rather, we want to think of them as arrows. Because in sciences and stuff, typically vectors represent velocity, things that sort of relate to motion somehow. And so E1, I want to imagine as this vector, this arrow. Okay, it's along the x-axis. E2, likewise, is a vertical arrow, like this. And what is E1 plus E2? Well, it's this specific vector, but geometrically speaking, all you do is you just adjoin the 2 vectors end to end, and that gives you the sum. Okay. Now, what is the span of this set? Well, I guess I do need a letter for this. Well, we talked about this on Wednesday too. Let me fast forward this a little bit. Well, the span, we can compute this as well, of course. But in this case, we had seen how, well, any point here, for instance, I can reach using only horizontal and vertical motion. In this case, for instance, you can just imagine this to be something like an Etch-a-Sketch. You have 2 knobs. One of the knobs sort of moves the thing this way. The other one moves it this way. You can go anywhere. So the span, all the places you can go from the origin using these 3 motions is everything. Okay, R2. But somehow, in a sense, this set is not optimal. In a sense that, for instance, I don't really need this specific vector here. Anywhere I can go using this, I can go using a combination of motions in these 2 directions. Okay? That's where this idea of non-redundancy came into play. We said, oh, this third guy is redundant. And in fact, maybe this is slightly harder to see, but possibly it would be better to say, out of these three, exactly one of them is redundant. For instance, instead of saying, oh, this guy is redundant, I could have said, this guy is redundant. If I had this motion and this motion, I could have gone everywhere also. Okay? So here, 1 out of 3 is redundant. Okay? And mathematically, what can we say? We can say, for instance, span of S, this set of 3 vectors is R2, but also, for instance, the span of E1 and E1 plus E2 is R2 also. This is the same thing as span of E1, E1 plus E2. You can write it like this, or if you want, you can write it like this. These are all the same. E2, comma, E1 plus E2. So one out of 3 in this set of vectors is redundant. Any comments or questions so far? What I really want to do is I want to relate this redundancy of 1 out of 3 vectors here to this condition. Okay. Now what I'm going to do is I'm going to use these 3 vectors and I'm going to adjoin them next to each other so that I have a loop. I start at the origin, and using these 3 vectors, I want to go back to the origin. So for instance, what I can do is this. Use E1 to move 1 unit. Okay, start at the origin. Use E1 to move 1 unit. Okay. In fact, let's use a different color for E3. Let's use green. Sorry, E2. Okay. Now, I started at the origin, moved 1 unit using E1. Now I'm at this point. Now I'm going to use E2 to move 1 unit. Okay. Now I'm at this diagonal point. And then at this point, what I can do is I can use minus this third vector that is in my set. It's an allowed motion for me. So I'm going to use that. If E1 plus E2 goes from here to there, its minus goes from here to there. So it's the same arrow, but flipped the other way around. So this is minus E1 plus E2. Question? Go ahead.
Wouldn't it be, oh, never mind. I see how you wrote it. I confused myself. You're good.
Yes. So this is what I mean when I talk about the loop. I started at the origin. I'm moving using only vectors in the given set. And I'm going back to the origin. Okay? Of course, algebraically, what does this say? This says nothing but E1 plus E2 plus this is 0. So 1 times E1, oh, I'll put it like this. 1 times E1 plus 1 times E2 plus minus 1 times E1 plus E2 is 0. Okay. This is my first scalar C1 in that equation, in that expression. This is C2. This is C3. You see, none of these numbers, in fact, in this case, are 0. So I have this. I was able to loop back to the origin. I did sort of like a loop. This is satisfied. But I was actually I was able to move actually. The coefficients are not 0. So this specific set fails to be linearly independent. In other words, it's linearly dependent, okay? S is linearly dependent, LD. Does this make sense? This is all there is to it when it comes to this idea. But as usual, what is the complication? The complication is when they give you a bunch of vectors that are not that easy to visualize. Okay, that's all the complication. That's where the complication comes from. And to handle that complication, you have only one tool ultimately. You need to reduce it to a system of equations, solve it, row reduce it, whatever. Let's go ahead.
I think I'm being silly, but you said it's linearly independent if we add everything together and we get 0, correct?
Yes.
But isn't that what we did? So wouldn't that be linearly?
You have to read the whole statements. Okay, that's why this is confusing. If this, then this.
If that is 0 and you can also.
I'm not saying and. If you move around somehow, you go back to 0, but somehow you do some math and it turns out that you actually never moved. Hypothesis, conclusion.
I think the statement that you said that confuses me is that you moved around but somehow you never moved. That doesn't make sense to me.
Like this is what we did right there. Like
Yeah,
we moved
because-
up there and then we moved back.
That's linearly dependent.
Yes. I'll give another example. Okay. Again in R2. It's kind of bizarre, I realize, yeah. Again in R2, let me this time just take E2 and E1 plus E2. It's a different set. Let's call it, I don't want to call it T because T is typically transformation. Let's call it Q, okay? E2 is 0, 1. E1 plus E2 is 1, 1. Well, in this case, we can just call it maybe V, this specific vector. Now, the claim this time is that this guy is linearly independent, okay? It's harder to visualize linear independence somehow this way. But the algebra still works, okay? Say C1, C2 are scalars such that C1 E2 plus C2V is 0. Okay? This represents some motion using E2 and V, and this says somehow using these two sort of magnitudes, you're able to go back to the origin. From here, to conclude that this set Q is linearly independent, I need to do some math and get that in fact these two anonymous numbers C1 and C2 have to be 0. In other words, even though it seems like I'm doing something here and I'm moving around and I'm doing a loop, actually I never moved. I just wasn't aware that I wasn't moving. Okay? So let's open this up. C1, 0, 1 plus C2, 1, 1 is 0, 0. Matrix algebra, or linear combinations, all that stuff. 0 here, and then, well, I'll just write it like this. C2, and then C1 plus C2 is 0, 0.
How'd you get there?
Distribute the scalar This is 0, C1. Distribute the scalar, C1, C2, C2. Add everything like this. You can, at this point, try to solve the system, but I hope you would agree with me that the only solution to this is when C2 is 0, in which case C1 has to be 0 also. Okay, and because from this equation I was able to go back to this, oh, I have some motion, I don't know what these coefficients are, but let's say that I did a loop and I went back to the origin. You do some math, you realize actually you never moved. You were just faking it. Go ahead.
And so if I tried to do this kind of reduction with the first example, I'd get maybe infinitely many solutions.
Exactly. Very good. We'll talk about that in a second. I want to match it with this, I want to match this linear independence to, solving systems. But before that, these two examples are very important, okay? Go ahead.
So the first example is linear dependence.
This one is, yes. This one, you see, you have redundancy, linearly dependent.
The second one is independent.
You have no redundancy, it is linearly independent. Okay, go ahead.
So this may be a strange question. If it's linearly dependent, what exactly is it dependent on?
They are dependent on each other.
On each other. Okay.
Yes. Another way to say the same thing, I wrote it here. Instead of seeing, oh, this set of vectors is linearly dependent, you might also see the phrase, there's a linear relation between them. So for instance, in this case, the third vector is just the sum of the other two. Okay. Any other comments or questions?
Are we going to talk about how to find out how many redundant vectors we have?
Yes. So for instance, perhaps I could give you this intuitive idea. In this case, you only have 2 dimensions in your ambient space. You cannot have more than 2 degrees of freedom. Okay? So if you have 3, at least one of them has to be dependent, actually. At least one of them is redundant, actually. Yeah. We're going to learn all this as well. Right? So this number, we're going to call, oh, this is the dimension of the space. But that dimension is also what you might call degree of freedom. In a space where you have 2 degrees of freedom, you cannot have 3 independent directions. Okay? Now, the same ideas work in the nonlinear setting as well. That becomes more applicable, but obviously, we don't really care about the nonlinear stuff. Any other comments or questions? One thing, so I wanted to do one more example with this independence and dependence, more complicated example. And in fact, let's perhaps try to write it down. Here's a more complicated example. Now we're going to have to use some algebra to figure the answer. But I'm going to use the exact same sort of translation between system notation and linear combination notation. Because you see, this again is a linear combination. So for instance, say V1 is 0, 1, 5. V2 is 1, 2, 8. V3 is 4, minus 1, 0. That's your set of vectors. You have 3 vectors in 3 dimensions, okay? In R3 if you want. If you want to be specific. The question is the set of vectors linearly dependent or independent? Well, I'm going to do exactly the same thing, okay? Set up this equation. C1v1 plus C2 V2 plus C3 V3 is 0, 0, 0. So that's the faster way of writing the same thing. I'm just going to substitute everything. But remember, this linear combination notation I can write in system notation, which I'll leave it to you. You fast forward it, it turns into this, okay? You have one column, second column, third column. Write them down. 0, 1, 5, 1, 2, 8, 4, minus 1, 0, and then bar 0, 0, 0. That's the augmented matrix. This set would be linearly independent if, just by assuming this and doing some math, you can get that C1, C2, C3 are all 0. This is what you want for linear independence. But in terms of the system, this is nothing but the solution. So you want to do row reduction and deduce that the only solution to the system is 0, 0, 0. Solve. And indeed, it turns out, you do row reduction and everything, and ultimately, it does turn out that the only solution is 0, 0, 0. And so that this set of vectors is indeed linearly independent. Okay. This I'm going to leave to you. It's in the textbook as well. It's nothing new. There's only one trick, okay? A linear combination like this is also the same thing as, so this is the same thing as writing V1, V2, V3, and then C1, C2, C3 equals 0, 0, 0. It's always the same thing. This is the one trick that we're going to use over and over. Go ahead.
I feel like the scalar C is more of the condition than a conclusion.
You mean this?
Over there, the definitions. Yeah. So if the linear combo is equal to 0 and the scalar is also equal to 0, then
You want to deduce that the scalars are 0. You don't want to assume at this stage, you don't want to say, oh, I'm going to say C1, C2, C3 exist such that this linear combination is 0. If you were to assume that C1, C2, C3 are 0, it's already 0. There's nothing to do. You want to say there's no other solution. There's a unique solution.
so that's the unique solution.
Yes. Yes. Okay. This is going to take some time. This linear independence is kind of bizarre. I'll say one word about this linear transformation business, okay? I want to spend more time on this, understand it. It's basically a function that distributes over linear combinations. So this is nothing but some t. It's a function such that C1, V1, blah, 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 CP, VP, or you just distribute everything. C1, TV1, dot, 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 plus CP, T, VP. In the second problem set, there's going to be a problem about this. I want to spend more time on this, but we're out of time, unfortunately. So we don't have class on Monday, Dr. King's commemoration and everything, but we're going to continue on tomorrow, on Tuesday. Thank you.